hear today from Professor Ben Britton, our cluster lead. He was the one who initiated and got this characterization at UBC cluster going. He is a professor in the Department of Materials Engineering, arrived here in 2021, and was before got his PhD in Oxford and then was at Imperial College and has been for a long time now working on all matters electron microscopy, but with a focus also on EBSD methods. So I'm sure we will hear a really great talk about what's new and upcoming in this field. And so he will talk about discovering materials with electron backscatter diffraction. Thanks.
Thanks, Annette. Just checking. Yes, mine is behaving as well. Checking my phone. Hi, folks. Welcome to talk on discovering materials with electron backscatter diffraction, where I'll give a bit of a background for people who are less familiar with the technique, and then a few of the directions of travel that we're working with at UBC and with partners elsewhere. So the question we ask ourselves is often, why are we interested in the microstructure of materials, and specifically, where can techniques like electron backscatter diffraction help us? We know, for instance, when we build a building, the shape and structure of the bricks, as well as the cement between those bricks, is important to the integrity of the wall. The same is true of every material that is crystalline at the nanomillimeter and in between scales. So we want to understand from, for instance, a manufacturing point of view, we'd like to control the grain size for our manufacturing process. From a science perspective, we might be interested in the grain shape because we might be interested in perhaps the fracture energy of a particular grain boundary or interface in that structure. We also want to know the distribution of phases. So many materials are made up of different crystal structures, and we'd like to know perhaps the volume fraction and the location of those grains or phases, and we might want to know how they evolve during a test or in between processing steps. We're also very, very interested in the crystallographic grain orientation or texture of a material. If any of you are drinking a soda can, the reason why that material is so thin, which reduces the cost of the packaging, is because the texture was controlled and optimized using electron backscatter diffraction. Alcoa was one of the first companies to employ this to affect and improve the deep drawing and earring process for aluminum drinks can manufacturing. Nuclear power plants do not work properly if the crystallographic texture is wrong. There are many, many other examples. The texture and microstructure and grain structure, from my perspective, are influenced through the processing of the material. We can fabricate these materials in lots of different ways and manners. And for instance, one of the things we might do is heat and beat or thermomechanically process the material to look at the strain path and the deformation. If you're an Earth scientist, the planet Earth or other planetary bodies are heating and beating materials through, for instance, the movement of plates through the material system. We can also have other boundary conditions, heating and cooling, where we might get precipitation and grain growth, where we are moving systems perhaps through metastable phases and structures in those parts. And all of these properties ultimately influence the final properties of the object or component. So many of us like to think that a metal is a lattice of positive ions that are behaving themselves beautifully. Most of the properties of those metals are controlled by the defect. And one of those, for instance, is the grain boundary. It's the motorway for diffusion in those systems. It controls strength, ductility, toughness, hardness, stiffness, electrical properties, oxidation, corrosion. All of these things can be thought of and can often be related to the microstructure of those materials. So we would like to have a technique that enables us to map that crystal structure within the scanning electron microscope. The scanning electron microscope, as described previously, is a very convenient instrument. It enables us to dial between millimeters and nanometers in the same tool. It's relatively friendly for our material systems for these. And we'd like to be able to map this quickly and get data that is useful and accessible. So we'd like online systems that enable us to do this quickly, so we can often move on to the materials or other problem that we're interested in, rather than the science of the measurement. I'm of course fascinated by the measurement, but I appreciate that accessibility is important, and EBSD has spent maybe 40 years developing that accessibility to make it a really underpinning technique in many laboratories worldwide. So if we just look at one example of an EBSD map, so this is a simple example of interstitial free steel. It's a fancy way to say we've got steel where we've locked up all the carbon, and this enables us to make the hood of a car beautifully shiny. You put carbon in the steel, it produces Ludus bands, and they put streaks in the front of your car, so you don't get paint adherence and other issues happen. In this material system, it's a body-centered cubic metal. We have effectively an ensemble of different grains, and I'll discuss briefly the different color coding, but for those of you who are less familiar with the color coding, we're measuring at every single point in this map the orientation of the unit cube. The fact that it is very blue in this map tells me that the 111 crystal direction is pointing along the z-axis. So the points of the cubes are pointing out of the plane of the page. And for instance, things like the stiffness of the system can vary by 30% based upon the crystal orientation, just due to the change in bonding in that material. We can also see that this has different shapes and sizes as different friends and enemies or grains of different orientation that could cause different mismatches in properties locally, which could be important if you're looking at fatigue of that material. You're looking at what happens under vibration, ultrasonics, etc., etc. This is scale bar is 75 micrometers. So we're mapping a reasonable size area of this material, and we're collecting that data and presenting it in a way that is, well, if you like, neon aesthetically pleasing, but at least enables us to interpret this data very quickly if we so wish. We can use this to look at other material systems. And so in this example, this is from colleagues at the National Physical Laboratory in the UK. It's like the standards lab for a lot of their processes. Manufacturing is really important to all economies, and cutting tools enable manufacturing to happen. One of the key aspects in the tungsten carbide cutting tools, they're hard metals, is the grain size, shape, and distribution. That tells us about the life, the heat transfer, and the efficiency of that tool. So they've been working over many years to develop standards to understand the population of grains in that material, how you sift and mix those different raw precursors, how you then put things like cobalt and chromium binders into the system to create a material that is both strong and tough, despite it being made of a cemented carbide in that system. And so we can now get a huge number of grains that are mapped that enable us to access really great contrast. So we can segment each individual grain, and we can count the size and shape of that individual ensemble. And we can apply then statistical analysis. These are the cumulative distribution functions to ask us, what's the distribution look like? It's not a single number. It's described by some population where we have something like a skew distribution for that particular population of grain sizes in this two-dimensional section of the material. We can use this to look at, this is from my own work, looking at aerospace grade materials. And so here we're looking at a titanium and molybdenum alloy. And this is just a really nice example to show you that we can map the balance of different crystal phases. We have a molybdenum-rich body-centered cubic phase. We have a hexagonal titanium-rich phase. And we can see the diffraction patterns at each point are different, but the computer has solved this for us to tell us about the phases. And we see this beautiful microstructure appearing that we can now, within the software, pull apart to look at the microstructure of the beta phase, the microstructure of the alpha phase, and you can start to see orientation relationships inheriting between those two structures, because it's a solid state phase transformation where the BCC high temperature phase transforms to a room temperature HCP phase, and you get inheritance of the basal plane to the 110 plane and the close packed A direction with the 111 direction in the BCC. And that controls things like how slip progresses through that system. And that's super important to stopping airplanes braking, which many of us like to fly occasionally, and we really like our planes to deliver people from A to B. So we've got a few little tasters of examples. I have many, many more, but I wanted to keep this talk sort of light in terms of giving you a flavor. We can chat about different examples if you so wish a bit later. But I wanted to give a bit of the sort of theory behind how the technique works. So fundamentally, we're going to use the scanning electron microscope to move the electron beam across the surface of our sample. And we're going to synchronize the collection of a two-dimensional diffraction pattern at every single point within this map. We're then going to use online, typically, algorithms to identify the crystal structure. This is a body-centered cubic pattern, and the crystal orientation. And that's the orientation of the cube with respect to a reference crystal direction. And then once we've done that classification of orientation phase, perhaps pattern quality, and a few other metrics, we can then reconstruct a map to describe that microstructure. And then we can look, for instance, at regions of common orientation and call that a grain. We can look at the interface between those and look at the character of that boundary. So we do this many, many millions of times in a typical experiment. And so we take our diffraction pattern that we collect. And the cool bit about EBSD is it's kind of like we have a globe of diffraction that is oriented with respect to a reference crystal. As we spin the crystal, the globe rotates. And so the projection of this globe on the screen, the gnomic projection, rotates as the crystal rotates. And the computer solves the problem to go from the crystal orientation, crystal pattern, to the phase and crystal orientation. And there's some clever algorithms, depends on your vendor, but we'll see at least one of them shortly. The fundamentals of the diffraction pattern, hopefully many of you are aware of Bragg's law, one of our favorite laws in diffraction, n lambda equals 2d sine theta. This says that if we have an incident energy radiation, this is our electron kV of the beam, corrected into wavelength eventually through the de Broglie equation, etc. We can then relate that to the crystal plane spacing and a diffraction angle of that particular species. Many of you are familiar with that for X-ray diffraction or spot diffraction methods. In EBSD, it's a subtle different problem that we shine the electron beam into our crystal, and effectively, if we have the crystal plane running, these black lines are the crystal plane, we can have this center line, which is the direct projection of that crystal plane. And Bragg's law, if the reflector is allowed, Bragg's law says we'll see a band of raised intensity between this angle 2 theta. So we have a bit of geometry, we have the electron beam, we have the crystal orientation, how it presents the band center, we have the plane normal running up here. And so if we know the position of the sample with respect to the screen, and we know which plane is which, we can then relate that plane to a reference orientation. Pretend I have two left hands. And that's what the computer's doing for us. And so we see that the band center is described by the diffracting plane. Effectively, it's perpendicular to the plane normal and contains the electron matter source point. We have the pattern center, which describes the distance of the sample from the detector and the position of the interaction volume with respect to the detector. It's a calibration bit of geometry that's important. And then as we rotate the crystal, we can see that band is moving across the screen. And so we can then solve the problem once we know the band. We just have to it's a bit annoying maths. We solve an inversion matrix to work out the rotation matrix between a reference crystal and the test crystal at every single point. In practice, we see this band of this center of raised intensity and the edges. In 3 dimensions, of course, this extends as we sort of expand this into a circular band on our sphere. And we see the separation of the band edges, 2 theta, and anything within those dashed lines are our bands of raised intensity to a first order approximation. And this is showing it for a particular 100 type direction in my cube. If I then expand this across multiple crystal planes, we can build up our crystal Kikuchi sphere. And this is a simple kinematic case with all the bands indexed. And of course, we can do more fancy maths to give us the cool sphere I showed you earlier if we require. I can discuss the fancy maths, but it's unimportant for today's discussion per se. In practice, we get a few more little details that happen. So we get the raw diffraction pattern looks like this. This contains effectively a diffuse background where the electrons have scattered and lost way more energy. So the electrons in the Kikuchi pattern have lost at most a couple of eV off the primary beam. These ones are typically higher energy loss electrons. But we can just collect a background or work out what this background looks like and divide one by the other, and we get this beautiful diffraction pattern that shows lots of information about the crystal structure of where the matter has interacted. The electron has interacted with the matter. To collect the backgrounds, whoever's teaching you how to do EBSD will suggest it for the particular system, but you often use like an amorphous region of your sample to get the background. You might rotate the crystal while it's collecting to blur the bands. You might do something across multiple grains, or you might do some maths to remove like a pseudo-Gaussian from this. So a whole range of different ways that you can solve to remove a background, and effectively flat field to make the maths easier on identifying the bands themselves. We have a little bit of this projection maths. It's kind of weird, but if we move the detector further away from the sample, the practice is this pattern will zoom out in here. So we'll see that effectively this angle between these two poles is fixed, and effectively as you pull the detector further back, you start magnifying the pattern. So we need to know that distance. And as you move the source point effectively up and down, this pattern would move up and down and be tied to that source point. So we just have to calibrate. There are lots of ways to solve this problem as well that are pretty trivial. Most systems now come with a preset calibration routine that's very robust for many applications. And then with a computer, we'll do many of these calculations per second, but effectively we can collect a raw diffraction pattern. And then the trick is we want to identify which crystal plane is which. Once you work out which crystal plane is which, you just sort of sort the problem properly, and you can work out the crystal orientation. To work out which crystal plane is which, some clever people in about the 1990s realized that you can use, there are two similar mathematical formulations, the Huff or radon transform, that effectively transforms a straight line into a peak, and the peak now contains a bright center and dark edges. And if you find that peak, computers like finding single peaks rather than diffuse bands. That's just the simple bit of how searching spaces work for that. So the Huff transform was pioneered often in this. It's now used by fancy cars to drive and stop you driving off the road. So the Huff transform is used in finding roads. In that. So this is the more formal case. Effectively, we have a band of raised intensities. So we see this yellow. The mathematics of this, the details aren't too important, but this is what we call effectively, get the right around, this is the angle rho. And one way to think of this problem is effectively to take a perpendicular line and then integrate the entire pattern perpendicular to that line. And then if you have a band of raised intensity, it will appear as a spot when the integrating line is perpendicular to the band. As soon as that integrating line is slightly off, then this starts to smear and diffuse across many pixels in your accumulator array. And so you see the yellow line sits here. So we have the angle theta across in the x-axis, and we have the position from the origin in the y-axis. So rho theta space is what's present here. And we can then work out which plane is which. It's a bit annoying to do, but it's possible. So now we can work out which plane belongs to which. This step that I missed a slide from, it will appear in a minute. One of the tricks is that no matter the orientation of the crystal, the angle between the planes is the same. So if I can find multiple planes, I can work out their interplane angles, and I can use a lookup table to work out which plane set is present. And so there's a few methods to use that, but it's just saying that the angle between my fingers is invariant of the orientation of my crystal in this case. So we've indexed, we can work out which crystal plane family is, and then we just sort of start the problem and say, this is 100, and then we can work out all the rest of the indices. And the computer does this very quickly. You'll see it in a minute working. If you are interested in the nerdery, we published a fully open source algorithm for this, because for a while there weren't any out there. It's called Astro EBSD. You can get some MATLAB code and it will talk you through it. But effectively, here's the raw pattern. Here's a Huff transform. Here's the peak identification step. And then once you've done that, you work out the bands, you work out the orientation, and you then can relate the crystal pattern to the crystal itself. And that's what you do at every single point in your map. So we do this many, many times, and our EBSD experiments are now operating often at 100 patterns a second, up to 16,000 for some systems these days. So many, many measurements in a finite time. So this is a simple example. We'll see this sample live in a short moment. But effectively, we can use the EBSD detector to collect the signal like a sort of backscatter diode. And so we call this a four-scatter diode image. And so this is showing me I have a grain structure. In this image, I've actually said nothing about the diffraction pattern. I've just collected different portions of the pattern to measure and assigned red, green, and blue to the different areas. So we get a nice picture to show grains. And then I've indexed each of the diffraction patterns, and I can get the crystal orientation. And for every pattern, I can tell you how sharp the pattern is. So that's the pattern quality. It's like a Fourier transform power spectrum type number. And then in this case, when I use a direct electron detector, a new advance we have at UBC, we can also measure the median electron count. So we can count the number of electrons hitting our detector. And this is our diffraction pattern that was used for this experiment in here. This whole map is 500 by 500 points, and it was collected in 2.3 minutes for this data set. This is a slightly bigger map. So this is 1 millimeter by 0.5 millimeter, 500 nanometer step size. It was collected in this case at 1244 hertz, 27 minutes, and now shows us a huge number of grains from our nickel example sample as presented. We have the IPF, the colors of orientation, and then we have some FSD colors to give us microstructure and quality, and this is the setup that's presented there. So I thought I would do, I think the first in our series of this is I was going to remote into the microscope and show you what's happening on the microscope, because I thought that would be more fun. So this is the Apreo Chemisem that's located on the 4th floor of Frank Forwards. Normally we would sit in front of it, but if you have it set up beforehand, you can. This is the primary electron column. This is my sample sitting here. This is a nickel disk, the one example. This is my EBSD camera inserted. This is my map. It's not hugely in focus because I set it up at 8 in the morning and then didn't get time to realign it just before we started. The horizontal field width here is 150 micrometers in this case. I can then shift to the second screen. Here. And I can just, this is my map. This is the software that's running. I've told it that I have some nickel in this. So I've told it from a crystal information file or the standard databases. And then I can say I want to go into map acquisition. I define an area within this. And here I'm just running something. It's 293 pixels by 200 pixels, 500 nanometer step size. And I'm running this. I've set it up sensibly. And it's now running, hopefully, at 2,000 patterns per second. So I can hit start. And we hope it behaves itself. And it does. And so these are our diffraction patterns. All of that maths is being done. It's being indexed on the fly on the microscope. We can save the patterns to disk and do fancier stuff if we like. And here is my microstructure appearing in real time. It took about 20 minutes, less than 20 minutes to set this experiment up this morning for that. And yes, I do know what I'm doing. I hit auto a lot to save myself a lot of time. The system is beautifully set up to do this nicely. So this is then doing a little bit of maths behind to show us some stuff. This is not cleaned up data. It's not quite in focus because it drifted, so gray mandies look a bit wide. But we can then see those different maps as presented in the microstructure. We can just see, just for the sort of thing that's useful as well, I can get some beautiful patterns if I just set this up to be slightly longer. 1 second exposure, single pattern acquisition, click a point. It will just take a second. And that's now my double diffraction pattern. Why do I hit near grain boundaries? There's a single diffraction pattern as presented, and the detected bands and the pattern center. So that's the pattern that's collected. This is on a direct electron detector. So this is using a Timepix 1 detector for this particular setup. And of course, we can see that this is clearly related. This is the orientation. This is the simulation. This is that sphere, similar to what I showed you. We made the sphere before they did, just for the record. And then this is the crystal orientation. So That's a 50 micron scale bar for this case. I can make it smaller, but the microstructure is not interesting. So, mapping the whole surface with a step size of 500 nanometers for this experiment. The step size smallest I would like to do is 20 nanometers, and the largest on this microscope in this configuration is about 2 millimeters across the surface. And the surface is, so metallographically, not very smooth. This is showing you topography and a backscatter, but it's very crystalline. So we polished it carefully, and then there's slight roughness because different grains have different polishing rates in that sample. This is the demo. This is the one that always works because I don't want to mess stuff up. It will hopefully look like this if you do your own experiments, but just to temper people's stuff, we spend a fair bit of time dealing with sample prep, and we have lots of experience in that space. We can train people to use this in about 4 hours. So if you've never used an SEM, 2 hours on the SEM and about 2 hours of EBSD stuff. So just for selling things of that. It's charged to access, of course, but that's not too expensive. So we've gone to the microscope. So let's just look at some future directions and other bits and pieces. So some more research active work that we've been playing with. And so this is the example that I've shown you, and this is building the work of Tianbi Zhang, who's about to defend his PhD. And so we can basically put the electron into a sample through a beam, and we can choose how the detector is presented. This is the example that you've seen in a regular EBSD setup with our commercialized system, and we have a partnership with Thermo Fisher to develop this and other variants of the EBSD technologies. In Tianbi's PhD, we've actually done a series of different setups. So this is in a reflection pair of geometries. So you have EBSD in the blue with the sample tilted towards the detector. Coming in December, we'll have EBSD running in flat configuration, so no tilting of the sample. And we now have a large backscatter pixelated detector quad pair called RKD around the pole piece. We can also set our SEM up as a TEM, and we can set up an electron transparent film, and we can use an on-axis TKD detector. So we put the EBSD detector below the sample, or we can run a regular EBSD detector, but just move our sample upwards with regards to the detector, the so-called off-axis geometry. And EBSD is just a matter of geometry. If we can get a pattern, we can work out what the orientation is. So this is the transmission Kikuchi diffraction as first introduced. Well, it was by Keller and Geis. There's a really lovely review by Snedden from the Australians in 2016. And this is now pushing us, this enables us to get between 2 and 4 nanometer step size in a TEM lamella. Very accessible because an SEM is significantly cheaper to operate than a TEM, just in terms of training, access, and a whole range of bits and pieces. So that's the sort of setup that what they showed sort of worked. We did this, and we used a series of compact detectors. So this is our detector. This is what we're getting. This is our TEM on-axis TKD detector, and this is an off-axis TKD detector. And so we did this work. It's been published in Materials Characterization. And we have our own software algorithms to do all the indexing stuff that we can just run all the stuff through. And here we have the raw patterns. Here we have the diffraction patterns background corrected. And then we have the index diffraction patterns for all of those geometries. So we can see that there are benefits and disadvantages to the geometries. And what we can do is we can take each of these experimental diffraction patterns and put them back on the reference sphere. Here we present it in a so-called stereographic projection to make it flat. But effectively, blue is what we saw in practice. And then we can play a cheap game of origami. And we can apply the 24 symmetry operators to effectively fold the fundamental zone to use the single shot of the experiment, slightly single, a couple of shots, to reconstruct a fully experimental. So no simulations were harmed in the making of this column. And then from those experimental full diffraction patterns, we can then get the same orientation and compare and understand what happened in the sharpness and other bits and pieces. Just because people are interested in nanoscale, we can also do the TKD, and we have a few developments in this area, but this is just one example that Tianbi kindly we're happy to share on this. So here's the collected data, here's the background corrected data. This is just looking at a bicrystal in aluminum, and we're just showing that we can get the diffraction patterns and indexed all through the standard routines to produce useful maps. It took, I don't know, probably an hour just because it was our home-built system. It's now far quicker. The indexing took far quicker because we just said, index it like your other friends, and it worked. So, some of you are interested in 2D materials. So this is a new piece of work that's just been published in ACS Nano. And so using this reflection Kikuchi diffraction, so this is the quad detector sitting below the pole piece, we can now show the orientations of tungsten diselenide. These are, we have two regimes. We have many sheet layers, so something between 20 and 60 layers supported on a grid. And then we also got diffraction patterns from, these are from the many layer problem, so 8 to 10 nanometers up to 90 nanometers. We see microstructure across this flake. There's different regions, there's a grain boundary and a few other bits and pieces. And we use some posh statistics or machine learning to help us decompose the characteristic signals for this case. We can also get it from single layer, 2 layer, and 3 layer. And because people don't trust diffraction people to get 1 or 2 or 3 layers, we can verify that with photoluminescence to check the layer thickness, because tungsten diselenide has different PL effects in thickness in this case. This is all in flatland, so we've been looking on the surfaces of materials. I'm now going to show some work from Ruth Birch and using the plasma FibSem. Some of you saw a little bit of this related work at the full school. But effectively in 3D EBSD, what we now do, many of you like reading books. Hopefully you all like reading textbooks. And you read a book by reading page by page. In a 3D EBSD experiment, what we do is page by page, we remove the surface of this material. So we use the focused ion beam, it's a xenon probe, to remove the surface layer, remove typically between 2 and 200 nanometers for each slice. And then we EBSD the clean surface, and we repeated this experiment many, many times. This is a very early experiment, so it does look way better in the newer stuff, and Ruth has some super exciting, very large data sets, but this is one that we're very happy just to show the taster for you folks of what you can do. So this is how we set up the experiment. We go towards the edge of the sample for this particular example. We create some space so all the diffracted electrons can escape towards our detector. We then look at this surface, and this is what it looks like. You get little, what we call curtains in this case, due to the surface hardness with fibbing. And then after you have done the 3D, your sample has vanished into the ether because you fibbed it away. So it's a destructive technique in that case. And this is what happens as you're reading the books in the microstructure. So we're going through. This is the surface. This is the band contrast. This is then the microstructure as indexed of that. So we can start to see that emergence of the 3D microstructure to start looking through that object. I need to make this one faster. It went on a while. So when you take the data, you then take it, you build a data pipeline to take it from the microscope in eventually into Dragonfly. Dragonfly enables us to do 3D viz segmentation. We can then mix that with our crystallographic codes in MATLAB. And then this is effectively what you get as a 3-dimensional object. So I thought, oh, I don't have the video one. I can find the video in a minute, but here's the 3D object as reconstructed, and we can now pull out different grain structures and a whole range of bits and pieces. This is 500 slices. Each slice thickness is 100 nanometer. The step size in each plane is 100 nanometers for this object. And we've reconstructed to give us a 50 micron by 50 micron by 50 micron cube. The newer data sets, we vary between like 20 micron up to maybe 250 micron if we're on if it's a good day. It might not be 250 in thickness, but certainly it's possible. We can also do site-specific lift out for this. So that was on the edge of a sample that can restrict what you're doing. This is from Shuheng Li's work, working with Ruth and Warren Poole. And Shuheng Li is interested in indentation in magnesium and local deformation. So here's an indent. And what we do here is we basically have the indent. We place this entire picture inside a little coupon. And we basically take the coupon and we put it on a stick. And then we stick the little coupon on the end of a post. and then we remove the layers of the post. And this enables us to go into an object and pick a region and say, we'd like to look at that piece. So we can do that all on the PFIB. The sample gets mounted in this interesting geometry, sort of sticking up here, and then we can do FibSem without moving the sample between each stage. And that enables us to get out this object. And so this is what we show in this case, 130 micron by 75, and then we got about 90 deep. What was frustrating, this was a bit of a failed attempt in some regards, because for the indentation, we wanted to have a nice big grain where we were testing the mechanical properties of only that grain. Unfortunately, we found some friends subsurface. So you sort of dug down and found the bedrock, and that was a bit annoying from the mechanical problem, but it shows nicely that you get three-dimensional structures, and we are aiming to publish. We have a preprint in here of all of the prep route to get you here, because that was quite a lot of work to get that to behave. Good for time. So I just wanted to say things that we can do at UBC. So I've given you a flavor of a few activities. I have many more that we've worked on, so happy to have some discussion about this. One of the things that was hinted at is sample preparation is important. I am a stickler for not cleaning up our data in our group. We like to look at the raw data, and all of the stuff that you've shown, I think, was raw. There weren't many scratches. We spent a lot of time thinking about sample prep. And this is important because EBSD is about the top 20 nanometers. Actually, as we go down to, say, 8 keV EBSD, it's even smaller. It's dependent on the sample geometry and the Z number of the material, but it's very surface for a technique. So an oxide layer, a deformed smeared surface, or carbon on the surface can mess up what you're doing. So we really want to avoid surface preparation damage. So we do metallographic polishing. We look at cleavage surfaces. We look at as-grown crystals. We use ion beam systems. We use electropolishing. We use the FIB. It depends on the problem that you're working on. But sample prep is half of the knack. The thing here is that this sounds intimidating. It's unlikely you're the first person to do metallographic prep on your sample. So if you get an EDS polish, you can probably refine that to get it to an EBSD quality. And a few other bits and pieces, or we can borrow from another method. We're pretty good. We've worked on ceramics, functional materials, thin layers, 2D materials, a whole range of different ones. We have many mechanical polishing wheels. Typically, we polish with a final finish of 20 nanometer colloidal silica, 50 nanometer colloidal silica. We also have an argon broad iron beam polisher in this building called the PEX system. It's a very gentle surface sort of tickling of the surface. We also use electropolishing. We have a controlled electropolishing system over in 419 in Frank Forward. And we can also use FIB preparation, as I've shown you in this case. So a whole range of different sample prep routes. There's a whole lecture that we should do at some point on sample prep for microscopy in this way. There is a book that I really do stress that people should have a look at. There's Metallography Principles and Practice by George van der Voort, who gives a whole range of the theory as well as the recipes for these techniques. In terms of instrumentation, we now have, I think, 5 cameras at least at UBC. So in materials, in the electron microscopy lab, which I help lead, we have the Apreo 2 ChemiSem. That's what you just saw running live. That has a direct electron detector. And coming just before, hopefully, the end of this year, it will have an RKD setup. It's good for lots of things, but it can do low KV work that most other systems in the world can't do. And it also has TKD as well. On the Amber X, we have a symmetry indirect detector that can do large area EBSD, transmission Kikuchi diffraction, and 3D EBSD with the plasma FIB. Over on the Okanagan, the filter lab have a system on a mirror with a symmetry S3. And under Professor Renel Debosque's GELF, they've just got a Clara coming in with a symmetry S3 system. They have a huge amount of experience, in particular on minerals. So sample prep, etc. They are probably one of the go-tos for EBSD on mineral prep, I would say, to be cautious to my colleagues in the OS and others. There's a system in the Center for High Throughput for Nanometrics. Never can pronounce that quite right. There's a Helios 650. And then the QMI have an Amber with a symmetry S2, very similar to ours, but I'm not sure it's set up for 3D in that case. Data analysis, we have most of the commercial packages around on campus, but we also have a huge amount of experience pulling the data into a tool called MTech. And if you're interested, we occasionally run workshops on that. And there's a load of, there's a GitHub with introduction tool sets that will let you load your data for getting started. And so we can probably help you in that space as well. So this is the amber X. We've removed the electron column for convenience, but the EBSD is pointing off to the side. You're looking down the top. It says EDS and a few other devices. This is a large area magnesium map. So to do that indentation, it's like finding a needle in a haystack for the grain you'd like to indent. So we do the EBSD, we pick this grain, and then we go and zoom to it in the nano indenter, poke it, and then we take it out, and we then do lots of work afterwards. This is the 3D data set that I've just shown you in that. And then this is a TKD data set, and the scale bar there, that's 1 micron just for that scale bar. There's that little field, and the whole area was mapped in that foil. So this is a TM lift out that was done on the PFib on steel, I think, in this case, for that example. Oh, there's the slice and wipe. Apparently it does appear. So that's the 3D slice and wipe. Kind of nice. And then the Apreo. So we've seen this now live, but this is it physically what it looks like. That's the system with EBSD in. So we can do fast mapping, as I've shown you. We can do low kV. This is 8 kV in a dual phase titanium molybdenum at 65 patterns a second for that example. And then we can also, for certain problems, we want beautiful diffraction patterns. And so that's a silicon carbide. It's one of the sharpest patterns you can get in the world on those sort of systems for that. So to summarize, hopefully what I've shown you is that EBSD is just an embarrassing problem in that we collect a diffraction pattern at each point. But perhaps what's most ingenious about the technique is it's interpreted live. And that really increases your access to useful information. We interpret the phase, orientation, and crystal quality to build up rich microstructural maps. And these can do stuff like grain structure, grain boundaries, phases, parent phases, strain, in situ phase transformations, deformation, more and more and more. And we can interpret this data to interpret stuff across multiple scales between nanometers and millimeters to look at real materials. And we've used this, as I've shown, in many others: metals, alloys, ceramics, minerals, a whole range of other crystalline structures. With that, thank you very much for your attention, and I welcome questions.